the matrix M has eigenvalues 1 and negative 0.5. Find an eigenvector corresponding to eigenvalue of 1. Let's review how to find eigenvalues and eigenvectors based on this matrix. So let's find this one negative 0.5 and then corresponding eigenvectors. So eigenvalues and eigenvectors arise from the next situation. When it is given some matrix M, we describe some transformation. When this matrix acts, it means when a matrix multiplied by a vector, we get another vector. So it is given some vector u. It starts at the origin, and you know that coordinates of a vector is coordinates of the endpoint minus the coordinates of the starting point. But since starting point is 0, 0, coordinates of the endpoint will be the same as coordinates of a vector. So under given transformation, you get another vector which can be in absolutely any direction and of absolutely any length. But there may be such a situation when under given transformation, a given vector u becomes the same vector u but multiplied by some constant, some number or some scalar quantity. And what does it mean? It means that under given transformation, vector u becomes the same vector but of the other length. It may be in opposite direction. And if lambda is 1, it will be the same vector. It remains the same under given transformation. Or when we consider a line through this vector under given transformation, this line remains the same. And such values lambda are called eigenvalues, and such vectors u are called eigenvectors. And how to find them? You can see we can move it to the left and equate it to 0 vector. And you can see when we multiply this by identity matrix. Identity, it's just a matrix with ones on the main diagonal. When we multiply it by this matrix, it will be the same. It's similarly to 1 for usual numbers, but now we can factor out u, and it becomes like this: m minus lambda I multiplied by u vector is equal to 0 vector. Notice that I write u to the right, because in general for the product of two matrices, AB is not equal to BA, so it's not correct in general to write u to the left and then multiply by this matrix. And to find the solution, vector u, we should multiply both sides from the left by this matrix inverse. So it becomes m minus lambda I inverse multiplied by 0 vector. But you can notice that the answer is 0 vector. What does it mean? It means that origin remains the same, but it's a trivial solution. And to get non-trivial solutions, this inverse should not exist, and inverse doesn't exist when determinant is equal to 0. So we should consider the next determinant of m minus lambda I is equal to 0. You may use the next notation for determinant like this, or just straight lines, but not this. And I will show, but it's not necessary to write it in detail. What is m? M it's 0.2, 0.8, 0.7, 0.3 minus lambda 1, 1, 0, 0. When some scalar or number multiplied by a matrix, each element is multiplied by lambda, so it becomes lambda 0, 0, lambda. And how to subtract or add matrices? You just should do this operation for every component. So it's 0.2 minus lambda, 0.7 minus 0, 0. For corresponding at corresponding places. And you can see it becomes, this matrix becomes like this: 0.2 minus lambda, 0.3 minus lambda, 0.8, 0.7, and determinant is equal to 0. And what is determinant? Determinant is this minus this product minus this product. So it becomes 0.2 minus lambda multiplied by 0.3 minus lambda minus 0.56 is equal to 0, and it's called a characteristic equation. So to find eigenvalues, eigenvectors, you may start with this determinant is equal to 0, then characteristic equation, and you need just solve this. You can see it's a quadratic equation with respect to lambda, and you know for quadratic there are two roots. You may use calculator, discriminant, sum product rule, as you like. So let's expand 0.06 minus 0.3 lambda minus 0.2 lambda plus lambda squared minus 0.56 is equal to 0. Lambda squared minus 0.5 lambda minus 0.5 is equal to 0. Let's multiply by 2 to get 2 lambda squared minus lambda minus 1 is equal to 0. Discriminant b squared 1 minus 4 times 4ac, 4 times 2 times negative 1, which is 9. And roots are lambda 1 is minus b, it's what? It's 1 minus root d minus 3 over 2a, 4. So you can see it's negative 0.5, it's this value. And lambda 2 is 1 plus 3 over 4, it's 1, this value. And to find the corresponding eigenvectors, so let's consider this value, eigenvalue. So if lambda is negative 0.5, we consider the initial equation, and our matrix 0.2, 0.8, 0.7, 0.3 multiplied by some vector which is required, and let coordinates of this vector be x, y. You may use a b, u1, u2, it doesn't matter, is equal to what? Lambda, here it's negative 0.5, xy, same vector, the same vector. And we need to rewrite it as simultaneous equations. I'll show it in detail, but you don't need to write it in detail. So you can see it's a multiplication of two matrices. You remember that to multiply, or actually two matrices can be multiplied if the width of this is equal to the height of this. You can see it's true here. And the answer will be a matrix which will have height like this, as this, and width as this. So the answer will be a matrix 2, 1. And how to multiply matrices? We rewrite each column from this matrix. There is only one column as a row here, so it becomes xy, and it becomes, we multiply this by this plus this multiplied by this, so it becomes 0.2x plus 0.7y, and it becomes the first element. Then we do the same with the second row, and it will be the second element, so it becomes 0.8x plus 0.3y. So you can see it's 2 by 1 matrix. Just element is just the sum of two terms, but it doesn't matter. Is equal to negative 0.5x, negative 0.5y. And you can see that one matrix is equal to another matrix. What does it mean? It means that these elements are equal, and these elements also are equal. So it becomes what? It's plus 0.2x plus 0.7y is negative 0.5x, and 0.8x plus 0.3y is negative 0.5y. And you don't need to write this, you can write direct this. And let's simplify it. We can move to one side and equate 0, or to opposite sides, doesn't matter. So let's move it to the left. It becomes 0.7x plus 0.7y is 0, and the second, what, 0.8x plus 0.8y is 0. And you need to choose such values for x or y so that these two equations are true. And we need, or it's important, direction only. We don't need the length. The length of this vector doesn't matter here. So, and we should choose x, y as the least integers. You can see we can choose xy to be, for example, -1 1 or 1 -1, it doesn't matter. If we write -2 2, it also will be correct, it also will be true, but we should take it is suggested the least integers. And the second must be automatically true. If the second is not true, it means that there is a mistake. And notice that in general it is enough only one, but you may check the other, it also must be true. So the corresponding eigenvector is -1 1. And the next we consider eigenvalue of 1 and do the same. Mu is equal to 1u. So our matrix is what? 0 0.2, 0 0.7, 0 0.8, 0 0.3. xy is just 1xy. And it becomes what? 0 0.2x plus 0 0.7y is x. 0 0.8x plus 0 0.3y is y. And it becomes 0 0.7y, 0 0.8x, just move to the right, and what? 0 0.8x is 0 0.7y. And you can see we can choose what? For example, 8, 7. So 7, 8. And you can see 7, 8 for the second, it's also true, correct? So the second, or the eigenvector corresponding to the eigenvalue of 1, it's 7, 8. So for this problem, give your answer in the form AB, so it's 7, 8. AB are integers corresponding to the eigenvalue of 1. The next, a switch has two states A and B. Each second it either remains in the same state or moves according to the following rule. If it is in the state A, it will move to state B with the probability of 0.8, and it is in state B, it will move to state A with the probability of 0.7. Using your answer to A, or otherwise find the long-term probability of the switch being in state A, give your answer in the form C over D, where C, D are integers. First of all, you should understand that here it's about what? About probabilities of to be in some state, and it's about what? It's about transition matrix, which describe transition from a current state to the next state of a system. And such systems, or systems which will be considered, are called Markov chains. Why? Because a Markov chain, by definition, it's a system for which the next state depends on the current state only. And how to construct a given transition matrix? You should read it as from to, so from state A, B to state A, B. Notice that it's opposite to usual, for example, when you consider matrices and, for example, adjacency matrix. Adjacency matrix we read from to. Don't get confused. And if we are at state, or in the state A now, probability, we deal with probabilities. It is given if we are in A now to B, or we will move to B with probability 0.8. So this entry is 0.8. But we deal with probabilities, and if we are in A now, the sum of all our probabilities is always 1, so the sum of each column is 1 because total probability is 1, so we can find these entries 0.2. And if we are in B now, the probability to be or to move to state A is 0.7, from B to A 0.7, and again sum is 1, so it's 0.3. And you can see that it's absolutely the same matrix as it is given in A. And this transition matrix describes the next transition matrix multiplied by the initial state vector. It gives the next state vector, and this vector is in terms of probability. So if now A is operating, so initial state becomes 1, 0 in terms of probability, because if A is operating, it means 100% A is operating. B is not operating, so 0% probability. And if you multiply, you can see that it's again multiplication of matrices. You can see that after one transition, and one transition here it's 1 second. So after 1 second, there is probability of 0.2 that A will be operating, and 0.8 that B will be operating, and B is operating now. So initial state vector it's 0, 1. If initial is A may be operating with equal probability, so you should consider 0.5, 0.5. If you need find probabilities after 3 seconds, so after 3 transitions, you should consider t cubed multiplied by initial state vector to find final state vector. But here we should consider states after a very long period of time, actually after infinite period of time. And if we need to answer the next two questions, the first question is what? Find the long-term probability that A will be operating. And another question is during a long period of time, we can find a ratio in amounts of times that A and B are operating. Definitely it's approximately. Or percent of times that A is operating and B is operating during long period of time. Such two questions. And notice that it doesn't depend on the initial state. And to answer such questions, we need steady state vector. Steady state vector, it means that transformation applied to or acts on some vector and we get absolutely the same vector. It's something like limit. It's something like some equilibrium situation after a very long period of time. And how to find it? You can see that it's absolutely the same as a problem on what? Eigenvector corresponding to eigenvalue of 1. And there are 4 methods or 4 ways to find steady state vector. And one of them is to find eigenvector corresponding to eigenvalue of 1. And notice that when you consider such transition matrix, and when you find eigenvalues and eigenvectors, one of eigenvalues, it will be always 1. And for this quadratic, you may apply sum and product rule, but you know that one of the roots must be 1. So you can see that this vector is 7, 8. 7, 8. And we also can make this vector to be scaled to 1. What does it mean? You can see that 15 parts in total, so we can rewrite as 7 over 15, 8 over 15. You may multiply by 100% to get percent. Now it's in parts of 1. And you can see that ratio is 7 to 8. And what does this ratio mean? Ratio in time, so approximately a ratio in time, so that A and B are operating. So a ratio in amounts of time, in the amount of time that A, B are operating, is 7 to 8, approximately, definitely. Or 7 over 15, for example, if they operate 16 minutes, 7 over 15 times 16 minutes is what? 28, and 8, it's 32. So approximately 28 minutes A operates in 1 hour, and approximately 32 minutes B operates in 1 hour. And it's one question. And another question is, after a long period of time, there is a probability of 7 over 15 that A will be operating. And you can see this, find long-term probability of the switch being in state A. So after a long period of time, the probability that A will be operating or will be on is 7 over 15. And notice that this vector doesn't depend on the initial state vector. It doesn't matter A is operating initially, or B, or both with equal probability. Final state vector will be like this. It may be problems in terms of population, or in terms of amount of something, for example, in the amount of people. So after a long period of time, total amount of people will be distributed in such ratio, or such fraction will live in town A, such in town B, out of what total initial amount of people, which is constant, something like that. Let's consider other three ways how to find the steady state vector. Another way is just consider this transition matrix raised to very large power, this matrix M, for example, to the power of 50, and using a calculator you get the next: 7 over 15, 8 over 15, 7 over 15, 8 over 15, and there must be equal columns, and it's steady state vector, and you can see it is scaled to 1 in terms of probability. And here you can see that if you multiply 1, 0, if initial state is 1, 0, you get this, or if it's 0, 1, you get the same. The third way is to consider actually this problem mu is u, it's steady state vector, how we write the equation problem, and consider simultaneous equations. It looks like this. Our matrix (0.7, 0.3) xy is xy, and again let's rewrite as simultaneous equations. It becomes 0.2 x plus 0.7 y is x, and what 0.8 x plus 0.3 y is y. And notice that such equations are dependent. It looks like x plus 2y is 10, and 10x plus 20y is 100. So there are infinitely many solutions, and to get a solution, you should add one more equation. What equation? That the sum of these entries is 1. It means total probability is 1 together with x plus y is 1. It's very important, otherwise you cannot get the answer. And you can simplify it. It becomes what? Minus 0.8x plus what? 0.7 y. Yes, it's correct, is 0. 0.8x minus 0.7y is 0, and you can see that this is dependent. It's actually the first, but multiplied by -1. X plus y is 1. Definitely you may solve it by hand, but it may be more complicated, and how to solve it with the calculator, with using matrices. Let's rewrite again in matrix form. It becomes negative 0.8, 0.7, 0.8, negative 7, 1, 1 multiplied by x. Y is 0, 0, 1. And how to solve it with the calculator? Definitely you may find the inverse of this, and then xy is what this matrix inverse multiplied from the left. But definitely you can find the inverse using a calculator only. So you may just enter matrix, one matrix, for example A, matrix B, and then you just calculate A inverse to -1 multiplied by B. You may try this, but I use another technique. We choose matrix, names A, oh no, we need edit A, and we need matrix 1, 2, 3, 1, 2, 3, 3 by 3, and entries are just enter these values. Negative 0.8, 0.7, 0, and 0.8, negative 0.7, 0, and 1, 1, 1, 1, 1, 1. You can see the first column are coefficients in front of x, the second coefficients in front of y, and the third is just values, numbers. And then again here we need the next matrix and mass, and we need this one RREF, and then again matrix, names A, and these values, this third column, or actually these two values, are our required values for x, y. 0.467 and 0.53. You may convert into fraction, but let's check. These are our 7/15, and 1 minus, so you can see it will be 8/15, same values. And the last method, it's to represent our matrix. We actually also need matrix to be to very large power, but we can consider this matrix to be to the power of n, and using a formula in the data booklet, and this formula says that it is equal to p d to the power of n, p to -1, and definitely it will be specified to use this method. Let me show. So p, it's a vector, it's matrix constructed on eigen vectors, and vectors are, for our notation, one is negative 1 1, 2 is 7 8. D is matrix based constructed on eigenvalues, and values must be on the main diagonal, so this corresponding to this must be here. It's what? It's 0.5. Yes, it's 0.5 and 1 and 0 zeros, and this matrix inverse. And if it's to the power n, it becomes to the power n here, to the power n here. There may be a question to show how this matrix changes with n, so you should keep n. If you need keep n, you keep this one, but anyway 1 to any power is just 1. Or if you need finally steady state vector, you can see that 1 to the power 1 just 1, but 0.5 value which is less by magnitude less than 1, it doesn't matter plus minus, or in between negative 1 and 1 to very large power, it's 0. And you need just find inverse. How to find inverse? We need determinant of this matrix P. Determinant of P, it's what? Negative 1 times 8 minus 7, it's negative 15. And inverse becomes 1 over determinant. We change these values, 8, negative 1, and change minus, and change sign for this, so negative 7, negative 1. You can see that we can multiply by 1 each in the matrix to avoid a lot amount of minuses, so it becomes like this, and just 7, 1, 1. It's a constant we can write in front, and we should multiply these matrices. So 1 over 15, negative 1, 1, 7, 8, and let's multiply 0, 0, 0, 1 by negative 8, 1, 7, 1. So we rewrite it in a row and multiply by, so negative 8, 1, so it becomes negative 8 by 0 plus 1 by 0, 0, negative 8 by 0 plus 1 by 1, 1. Next this 7, 1, again 7 times 0 plus 1 times 0, 0, 7 times 0 plus 1, 1. And now multiply by this. And again 0, 1, we get what? 7, 8, and you can see 7, 8, and 1 over 15 as a common factor, so it becomes 7 over 15, 8 over 15, 7 over 15, 8 over 15. And you can see we get the same steady state matrix and steady state vector. And notice that we can use method with eigen value corresponding eigenvector corresponding to eigenvalue of 1 when matrix is 2 by 2. It's not suggested to find eigenvalues and eigenvectors for larger matrices. And if it's a 3 by 3 matrix, the easiest way it's what? It's just to consider matrix to be raised to some very large power. You should just see that columns are equal, but to the power of 50 or 40 or 100, it doesn't matter. It's the easiest way. If it is not specified, you may just raise the matrix to the very large power, and you understand meaning of this steady state vector. If you should use or how to understand you should use this method, it will be clearly specified, and it will be clearly given. So there are 4 ways to find actually the same, the steady state vector. And again, this finally steady state vector doesn't depend on the initial state. And that's all for this question. So actually answer is let's write correctly the answer using the answer 2a, or otherwise find the long-term probability. Probability, it means we should scale to 1, being state A, since AB, so AB, this method you can see our steady state vector, and AB. So probability is that finally A will be operating in 7/15. State A. So finally A will be operating or switching the state A 7/15. And you remember another question is that approximately 7/15 over total amount of time A operates over a long period of time. CD positive integers. And that's all for this question.